Afternoon, everyone. We're taking a new tack. We are going to, oh darn it, well, I'm doing my windows. I'm getting paranoid with the windows. I lost my window. You try this again. There we go, right. We're going to do chapter 8 today, an introduction to random variables it's called. In particular, we're going to look at a probability distribution. And basically what that is, it's a table where each event has its probability recorded. So, I'll give you an example. This is a version of question 1. And they do introduce things like x's, but that's just a placeholder. So there's x. And according to this, the only things that can happen, or I'm calling it x, let's call it k. K is 1, it can be 4, and it can be 5, and it can be 7. That seems a bit weird, but, oh, I don't know. Let's suppose that you've got 4 houses, 1, 4, 5, and 7. And what's the probability that x equals k? Right. The probability that you get 1 is a fifth. The probability you get 4 is a fifth. The probability you get 5 is a fifth. And you're being asked to find out what the last one is. So a probability distribution has the 4 things that could happen, right? You roll a funny dice, and this dice has 4 numbers on it. How about that's the story, right? It would be one of those tetrahedron dice, right? I don't know if you've ever played games, right? And it's got a 1, a 4, a 5, and a 7. And the way it works is it's loaded in some way. So the chances that you get a 1 is a fifth. The chances that you get a 4 is a fifth. And the chances that you get 5 is a fifth. And we're being asked, what's that guy? Well, one of the properties that a probability distribution has is that each of these things are independent of each other, right? They're not connected in any way, right? And so that's the probability a 1 can happen. And if a 1 can happen, you can't get a 4 at the same time, right? When you roll a dice, only one number at a time. And the second property is, what do all the numbers in a probability distribution add up to? 1. And if you add these guys, doesn't it come to 3/5? So by that logic, and it's the correct logic, do you understand why that's 2/5? Because this question was, fill in the last guy. Are we cool? Let's jump around a little bit. Let's show you what these questions look like, because it's probably easier if you see them than me just reading them out loud to you. Make this a little bit bigger. Okay, here's a probability where k, the thing, can be one of, what's that, 5 different numbers for whatever reason. And this is the probability that it's 150. This is the probability it's 0.2. Can you see that the missing guy at the end is going to be dead easy to calculate? Because don't you add up what you've got and see what's left? Well, if I add up what I know about, 0.3, 0.4, 0.56, 0.78, in this question here, do you agree 0.2 is what's left? These are called probability distributions. I would call them tables, but functions is fine. Probability distribution table. Now, here is another one. It's got a story attached to it, but what's missing? What is the last probability? What's the probability somebody get 25 questions right? Or he makes 25 questions? Right. Add up what you've got and see what's left. Anybody done it yet?
0.05.
I agree with you. Hey, compared to some homework, is this at least starting off nice and simple? Right. Probability distribution table. Right, now, a little bit different, but I'm glad I've got this in front of me now. Maybe make it even bigger. That might help. Well, for my eyesight, it does. So here is the X, the thing, the events, are the number of births in a day at a hospital. So in this one hospital, 0 births happened with a probability of 0.1, 4 births, probability of that, 7 births, probability of that. Now, X less than or equal to 3. Do you see that guy there? Aren't we talking about the probability that you get 3 or less births per day? That's how I would read that out loud. Now, if you go to this table, say again, Rob?
0.78.
I'm assuming that you added these 4 numbers that I've highlighted together.
Yes,
Does
sir.
that make sense?
Yes, sir.
Right. In which case, 0.78 it is then. And then it says explain the meaning of it. How about this is the probability that there will be 3 or fewer births. Now, if that had said equals 3, that symbol means less than or equal to. If this had said equals 3, wouldn't the answer just be 0.29? If it had said greater than or equal to 3, wouldn't we add up all of those guys? If it had said greater than 3, right? So if it had said something that looks like this, I'm just putting it here so you can see what I'm saying. If it had said that, wouldn't we only have added up those 4? Because isn't greater than 3 doesn't include 3. Does that make sense? Right. So from this table, you can ask all sorts of cool questions. And what would this thing mean?
Complement.
Yes. And what's the complement? I like to sometimes use the word opposite. Well, what's the opposite of getting less than or equal to 3? What's the opposite of getting less than or equal to 3 births?
Wouldn't it need to be greater than or equal to 3, or is just
Not equal to, just greater than 3, right? Only one of them gets the equals. So it would be actually greater than 3. So one of these should be, there we are. In English, I would probably phrase it, there'll be more than 3 births, which is not quite the same as that one, because in this one, aren't you 3 or more? And this one, just more. Right, so the extra word makes a difference. And I think I'm going to have to shrink this up. Yes, I will. Right, now we're going to look at questions where we have to build in question 4, what we're going to be doing is throwing a fair coin is tossed 3 times. So we're going to do a coin 3 times, and we're going to record X is going to be the number of tails. So X is going to be the number of tails out of 3 throws. Now, they even tell you what they are, so I'm just going to write them down. 3 heads, 2 heads with a tail going that way, 2 heads and a tail going that way, and 2 heads and a tail going that way. And then we had, we need a tail now. So I'll just write my one. I know what they're going to be anyway. We're going to do a head and 2 tails. So how about a head, a tail and a tail, a tail, a head and a tail, and a head, a tail and a tail. And lastly, we can have 3 tails. So these basically is the sample space. There are 8 events. Now, if I just take randomly this one, that's a tail times a head times a head. And the reason I can multiply them together is that these are all independent of each other. And can you trust me that you get an 8th? In fact, Can you trust me you get an 8 for all of them? Does that seem reasonable? So far, so good. Okay. So what we're now going to do is create the probability distribution. So it's going to be in the form of a table. And X is going to be the number of heads. And underneath, you're going to be the probability that X, the number of heads, equals K. So you can have 0 heads, 1 head, 2 heads, or all 3 are heads, right? And when you do that, then what you need to do is you need to find the probability of each of these events, and they're not the same. They're not a quarter, a quarter, a quarter, a quarter. Give an example. If you get no heads at all, isn't it just that one event there? So that's 1/8. If you're talking about 1 head, won't 1 head actually be these 3 events? So that's 0 heads, 1 head. And that ends up being 3/8. Now, if you do 2 heads, you get 3/8. And what's the chance that all 3 of them are heads? Well, that only happens with a probability of 1/8. And as a quick check, don't all of those add up to 1? So I know it's correct. Are you happy about how this eventually gave us our table? So you find all the things that could happen and the probabilities of those things, and then you fill them into your table. Actually, that's all they ask you for. So I guess the question's finished. Now, in the next question, I'm going to show you their table because it's quicker, hopefully. And here we have a probability distribution. 2 values are randomly selected with replacement from the list 1, 2, 3, and the chances of it happening is this. So I don't need to create this table. They've done it for me. So what's the probability that the sum is even? Well, that's even, and the number 6 is even, right? So do you see it's actually a combination of this guy, and this guy. So the probability that it's even is 1 plus 3 plus 1 more. So we're talking 5 nines. If they wanted to know the probability that it was odd, wouldn't it be 4 nines? And if you wanted to know that it was a 5 or a 6, wouldn't you add these 2 together and call it 3 nines, but then simplify it to 1/3? So if you've got that table, you can do any kind of relatively straightforward question involving combinations of things from that table. Have you noticed that you just add the individual bits together? So if it's even, you find the things that are even and add them up. If it's bigger than 3, you find the things that are bigger than 3 and add up the probabilities. So as long as you know what you're looking for, you add them together and you are good. The next question I'm going to create from scratch, a problem from question 6. And in this, there are 4 left-handed kids and there are 10 right-handed kids. And 2 children are being chosen for whatever reason. And the key word here, without replacement. Remember that phrase before, without replacement. I'm just writing all that down so that when I go to my whiteboard, you'll know where all the bits are coming from. Okay.
Professor, you muted yourself.
Evidently I did. Can you hear me now?
Yes.
Okay. Oh, this is weird stuff happening. Right, back to this. So 4 left-handed, 10 right-handed. See, 4, 10. We're good with that? Now the without replacement is going to kick in. This is for the second child now. They could be left-handed, could be right-handed, could be left-handed, they could be right-handed. The first child is left-handed, right? The first child you picked was left-handed. That means the world now only has 13 kids to pick from. And since you've used up one of the left-handed, it's 3 out of 13 and 10 out of 13. Are you happy with the change in the fraction because of the without replacement? Right, now if we go to this one, the first child was right-handed, so there's only 13 to pick, but 4 of those are left and the other 9 are right-handed. Are we comfortable with that? Now I'm going to do the probabilities then. Now I could have simplified those guys down. I chose not to. As long as I simplify the answer, it won't matter. So what's the chance that it was a left-handed followed by another left-handed? Well, you just multiply the 4 14s by that guy and you get 12 out of, I don't know, let's find out. 14 times 13, 182. And then I think I can simplify that if I do it on my calculator, and I get 691s. Then I'll just go through the next one. It's 4 out of 14 times 10 out of 13. That way is 40 out of 182. And I'll turn that into a fraction. That's 20 91s. This one here is going to be 10 out of 14 times 4 out of 13, which is the same number as that, so it's going to be 20 91s. And the last one is going to be 10 14s times 9 13s, which is what, 90 182. And that is going to be whatever it is. And that is going to be 45 91s. I'm going to put little circles around these guys, 6, 20, 20, and 45. What check could I make to make sure I didn't screw up at least one of these? What could I do with these to check that I did it right?
Add them up to see if they equal 1.
That's it, and 26, 46, and they do, so I'm happy. Now, we're now going to create the table, which is going to go here. And in my table, they're going to be K and the probability that X equals K. And in this case, X represents number of left-handed. So we're counting number of left-handed. So you might have no left-handed kids, one of them's left-handed, or both of them are left-handed, right? Now, if I do no left-handed kids, isn't that the same as both being right-handed? So that's the answer. Right, 0 left-handed is 45 91s. You happy? 0 left-handed or 2 right-handed kids. So 45 out of 91. If I wanted 1 left-handed, exactly 1 left-handed, wouldn't it be this one here and also this one here? Would you agree it be those two? They correspond to 1 left-handed. So you join those together and you get 40 out of 91. And 2 left-handed is probably the easiest to trace, 6 91s. And we've now created the probability distribution for 2 children being picked from this class without replacement. Now, there is, in the homework, they don't ask you to create that tree or even to fill in, that A, B, C, D thing that they did in other questions with the probability tree. They just gave you things like this. Don't know why that is there. No. And so, can you imagine that you would get these numbers and you'd put them in here? So that's how you kind of show that you knew how these numbers came about. Are we good on that question? Could you imagine another question with different numbers, but essentially the same theme? So we're now on to the last question, because it's a very short section, and that is question 7. Of course, you're keeping the best till last. I think it would be better if I then jump over and show you this question rather than say it. A woman decides to have children until she gets her first girl. She's like my sister Morag, who never did get a girl. She gave up. And so this woman decides to have children until she has her first girl, or until she has 4 children, which is exactly what my sister Morag did. Right? She gave up on the 4th one. Right? Well, fine. Whichever comes first, right? So if she gets a girl, she'll stop having kids. But if she doesn't, she'll keep going. But once she's got to the 4th kid, if it ain't a girl, it ain't happening, right? That's it, I'm finished. So it's quite a convoluted little story. X is going to be the number of children she has. So we're not caring. X isn't going to be how many girls she had or how many boys she had. X is just going to be how many children she had. So let's see how that works. Can we make the assumption, and that's what they're talking about here, that chance of a girl is a half and the chance of a boy is a half, right? 50-50. Now, first girl is a half. Would you agree that that's going to happen 0.5 of the time? And so the chances that she has one child is 0.5 because she actually got a girl. The first kid was a girl, she's happy, she's finished. Now let's look at the next one. She had a boy first, that means she had to try again and she got a girl. Well, won't that be a boy first times a girl second? Are you happy about how that chance of happening is 2 things independent of each other? And so the number is 0.25. And so that would represent 2 kids. Would you agree she had 2 kids before she stopped? Now, this fella here, would you agree it's going to be a boy, and then she got the girl and she stops? Now, wouldn't that be 0.5 times 0.5 times 1 more 0.5? And can you pretend that I did that? I'm going to do it with my calculator just to make sure. And it's 0.125. Now, what else could happen? She had 3 boys, and then finally she got the girl she wanted. So that would be 0.5, 0.5 times 0.5 times 1 more 0.5. That is 0.0625 if you do it. Or, like my sister Morag, she got 4 boys. And won't the chance of that being 0.5 times 0.5 times 0.5 times 0.5, and that's 0.0625. Now, this fella here, isn't that the only way that she would end up with 3 kids in her family? Now we're left with 4 children in her family. Now, how does she get 4 children in this story? Well, isn't there actually 2 different ways that she could get 4 children? So what do I do with these 2 probabilities to figure out what goes there?
Add them.
And if you do it correctly, what should all of these always add up to if it's a correct probability distribution table? 1. And guess what? They do. So we know we're right. So do you notice that you had to multiply things together to get the individual probabilities, right? The ones that go here, here, and here. But to get this last probability, didn't we have to take 2 different situations and add them together? So sometimes you multiply to get individual probabilities, but you may end up adding things together to get the probability distribution that fits in that particular box. Have we any questions, or is that going pretty good? I got one thumbs up. Are we good, guys? Then we are moving on, and at least it gives me a chance to do what's called the normal distribution. If WebAssign decides that it's going to load up. Oh, guess what it did. So this is going to be notes. Where are we? Chapter, forgotten what the number is, 8. The normal distribution. And we're going to do a little bit of revision because we've actually met some of this before. Here it goes. Now, we're going to be talking about in this story populations. And in particular, we're looking at population mean. And when you use populations, you use that funny little Greek letter. Does anybody remember how you read that letter out loud?
Yeah.
So we're going to look at population means, mu. And we're also going to look at populations standard deviation. And we use a letter that, it's a Greek letter that looks like that. Does anybody remember what that letter is called when it appeared?
Sigma.
Starts with an, yeah, sigma. So if I say mu, you know I'm talking about a population mean. And if I say sigma is 10, you know I'm talking about a population standard deviation. Okay? Just a quick reflection. Now, here's a guy that we've also met, z-score. And our z-score was data, take away the mean, and it was divided by the standard deviation. And when our data came from a sample, it would be data, take away the mean, divided by the standard deviation, right? Or sometimes I might have written it like that, right? How to get a z-score. Now, when you do populations, you can also calculate the z-score. And if you keep the formula generic like that, it just becomes data, take away the mean, divided by sigma. Do you see it's essentially the same thing? We're just using letters instead of words. So far, so good. So let's give you some examples. Suppose I have a population and the population mean is 0 and the standard deviation of that population was 1. And your data, we'll use X to represent the data. Your data was the number 1.6. If I asked you to calculate the z-score, couldn't you just say data, take away mean, divided by the standard deviation? Are you happy with that formula? And so the data is 1.6, the mean is 0, and the standard deviation is 1. And there is our z-score. Okay, call that question 1. Question 2, the mean is 100, standard deviation is 15, and the data is 112. If you want to get the z-score, data, take away the mean, divided by the standard deviation. Data, take away the mean, divided by the standard deviation, 0.75. We'll just keep z-scores as decimals as a general rule. So as long as I tell you these three things, are you comfortable with finding z-scores? Do one last one then, just to be sure. The mean is 70, the standard deviation is 5, and the data is 62. And we're being asked to find the z-score with this information. And the z-score is data, take away the mean over standard deviation population, 62, take away 70, divided by 5, and I believe that's negative 1.6. Isn't it okay to have negative z-scores? It's okay to have positive z-scores. And if you want to get an interpretation of what is a z-score measuring, in one sense, isn't it measuring how unlikely that data is to happen for this particular population? Aren't big z-scores unlikely events? In fact, what kind of z-score makes you an outlier? You have to be what number? You have to be bigger than what number? We might not have phrased it in terms of z-score, but it is z-scores. Last chance?
Greater than 1.
Greater than 3.
3.
Can you remember more or less than 3 standard deviations away from the mean? Remember that rule? Z-score is how many standard deviations you are away from the mean. So that's about 1.6 standard deviations away from the mean. And this one is just 1.6 less, but it's still away from the mean. This one's only, what, about 3/4 of a standard deviation away from mean. So if the z-score is, I guess it also goes the other way, doesn't it? If you're less than -3, if that happens, you're an outlier. Are we comfortable with the new notation? Well, maybe not so new, but sigma is standard deviation and mu is population mean, and that you can calculate z-scores when you're given population information, which is what these are. Any questions? Okay. Just do a couple more, call it good. The mean is 75, the standard deviation is 10, and the data is 100. Then the z-score, data, take away the mean over standard deviation, 100, take away 75 over 10, that ends up being 2.5. Let me phrase the question differently. The population IQ has a mean of 100, and the standard deviation of the IQs is 15. Is someone with an IQ of 141, are they an outlier? What we would probably call a genius, right? Is 141 an outlier? Well, let's find out. You get its z-score. And you take, 141, subtract 100, then divide by 15. Oh, do it on the calculator. Why am I putting a bracket around 141 take away 100? Why do you need that bracket?
To isolate it from the calculation, because otherwise the calculator is going to divide first.
Yeah, so it's to get the order right. And the answer I have here is 2.73. So is someone with an IQ of 141 an outlier? Agree? No. In a different story, suppose it was 3.18. Then yes. So Z-scores work with populations just the same way they work with samples. Same formula, same interpretation. And with our little hiccup, that is us for today. So your last name and bye-bye. And if there anybody wants to hang about to ask or tell me something, I will wait.
Thank you, Professor.
Right. And if you don't see me tomorrow, it's because I get cut off with power. And if I do, I will try and use my phone to contact you by email, but don't guarantee it because I don't think it would work, but we try. So if I haven't turned up in, what, say 10 minutes, give me a little break in case the power's off, then we'll just call it a day. Okay, bye-bye, guys. John, have you a question for us? John, are you here? Okay, going to stop this share for a minute. Stopping the recording. John, this is important. If you